We've been discussing Newton's second laws and forces and how they interact with objects in motion. And essentially, that's the study of dynamics. We've completed all three of Newton's laws and discussed those. Now we're going to do kind of following what we did with kinematics, where we discussed linear motion and the kinematic equations for constant acceleration, and then switched to describing things that are going in circles, which were hard to do with those linear equations. We're going to do the same sort of thing with dynamics now, and we're going to start to look at Newton's second law, Newton's third law, and all of those things when objects are traveling in circles, and we're going to call that circular dynamics. So the first thing we're going to have to do is consider an object going in a circle, and we know that when an object's traveling in a circle, it is not moving at a constant velocity in a straight line. So we have some object that's traveling in some, circular path like this. When that object's there, it's got a velocity going that way, tangential to the circle. When it's over here, it's got a velocity moving tangential to the circle that way. And even if it's moving at a constant speed, it's always, the direction of its velocity is changing. We covered this, we discussed this when we were doing kinematic equations and describing objects moving in circles, right? We know it has some component of acceleration, the centripetal acceleration towards the center of that circle as the object moves around. All right, so what does this all mean? Well, if we think about what we've been learning, right? We learned Newton's second law, which was the net force is equal to mass times acceleration, right? We can look at whatever object we're discussing, we can identify all the forces, do all those things we've been learning, and identify the forces that add up to make the net force. And then we can look at how the object's moving and what direction, and through that description of motion, perhaps figure out what the acceleration is. And that's the only sort of thing that comes into play here, right? If we know the object's moving in a circle at a constant speed, we know its acceleration is this centripetal acceleration. And we know that that acceleration is equal to v squared over r, where v is the tangential speed, the how fast it's moving around, and r is the radius of the circular path it's traveling in. And if we essentially, that's the only thing we're going to be adding for the next for today's video and the next little bit is getting comfortable with, how do we incorporate all those kinematic descriptions of how things are going in a circle into what we've just learned about Newton's second law. So what that all means is if we have an object moving in a circle, F net equals ma. Newton's second law still holds, but we know that that acceleration is v squared over r, and it's directed towards the center of the circle, right? So there has to be some net force keeping that object going in a circle. If there wasn't, that object would start to follow Newton's first law and continue moving off, shoot off the circle in a straight line at a constant speed. So when we have objects traveling in a circle, there has to be some component of the net force pulling it towards the center of the circle. And you can think about this if you've ever held a rope or something and spun it around. You have to pull with the rope with some tension to keep the tip of the rope traveling in that circle. All right. Similar though to what we had when we were doing kinematics, because that acceleration is changing directions as we move around the circle. So again, if we're here, we have an acceleration pointed that way. When the object's here, it's pointed that way. And in our x and y coordinate system, this acceleration is constantly changing, so it's not it's a difficult thing to handle in terms of kinematics and that. So what we want to do is we want to just define what we're going to do is define a new coordinate system that can kind of avoid that. And the coordinate system is what we call this RTZ coordinate system here, where rather than describing our x, y, and z, right, rather than describing some x, so in this three-dimensional picture, rather than describing some x, some y, and then coming off that plane some z, we're going to define an R, so a direction pointed towards the center of the circle. Come on, pointed towards the center of the circle. Some T in the tangential direction, and then some Z direction that's perpendicular to that circle. And this coordinate system will move with that object. So when it's on that side of the circle, R is still pointed towards the center of the circle, T is still tangential, and Z is still in the Z direction. So this coordinate system is going to make our lives a lot easier, because then when we break all our forces into components in these directions, what we're going to find is the acceleration in given directions are often going to be zero, and things are going to get sort of, the math and everything's going to get a lot simpler to deal with. So, if we have just some arbitrary object moving in a circle with some velocity v, it has at a constant speed and some acceleration towards the center of the circle. In that RTZ coordinate system, we have, R towards the center of the circle, T tangentially, and then Z would be coming out of the page. We have the acceleration in the radial direction is that V squared over R. That's our centripetal acceleration towards the center of the circle, or written in terms of our angular coordinate system, that omega squared times R. In the tangential, the velocities are zero in every direction except for that tangential direction. So when we have something moving at a constant speed in a circle, we immediately see that the accelerations in the RTZ coordinate system are zero tangentially and zero in the Z direction. So our F net equal to mass times acceleration becomes much easier to handle in this situation. The only coordinate where A is non-zero is the radial coordinate. And we'll see as we get through some examples and all that in our synchronous sessions that this makes our lives much easier. But again, everything we've learned about forces to date still holds true. Our technique for solving these problems, where we identify forces, draw a free body diagram, pick a coordinate system, all is the exact same, except for when we pick our coordinate system, we're going to want to use this RTZ coordinate system because it simplifies our lives quite a bit. So one of my favorite sort of examples of circular motion is just simply satellites orbiting the Earth, or even the Moon, or orbits of planets sort of things, right? Where you have some object that is at some height, and it's just floating through space, traveling at some speed in a circular path around the planet, like our satellites. And the gist is, a lot of people say, oh, it's weightless, or you don't have any gravity. You still have a force of gravity here. You're close enough to Earth that there is a significant force pulling you towards Earth, and you keep falling, so this object is falling and accelerating towards Earth. It's moving at such a speed that it misses Earth every time it falls, right? If it was going slower, it would crash into Earth. If it was going much farther, it would, careen off out into space and escape Earth's gravitational pull. But the gist is there's sort of a balance between Newton's first law of the tendency for the object to travel in a straight line and Newton's second law pulling, and the force of gravity sort of pulling it towards the center of Earth and causing it to turn, right? There's an excellent video on YouTube that's, let's just watch it right now.
Halley's question would change science forever. Through years of observation, scientists had discovered that the planets move around the sun not in perfect circles, but in slightly elongated elliptical orbits. But no one could explain why. Halley and many other scientists had begun to suspect that the planets were attracted to the sun by some kind of force. They guessed that this attraction became weaker with distance in a mathematical relationship called the inverse square law. For example, the inverse square law says that if a planet is twice as far from the sun, the gravitational attraction it feels is 4 times weaker. But no one had been able to prove this resulted in elliptical orbits. Several months later, Halley received a paper from Newton. It was Newton's mathematical proof that a planet obeying the inverse square law of gravity must travel in an elliptical orbit. Newton may have used calculus to arrive at this, but he had not published this new form of math, and his proof was written in the traditional language of Euclidean geometry. But Newton wanted more than a mathematical proof. He wanted to know how the planets moved through space. For the next 18 months, Newton worked on this question day and night. He barely ate. He barely slept. And he saw no one.
When you look at what he did during that time, it's difficult to believe that any one human being carried out this amount of novel mathematical and mathematical physics research.
Finally, he submitted a 500-page draft of his masterpiece, the Principia Mathematica, to the Royal Society for publication.
It is the greatest book of science ever written, bar none. It is the most magnificent work. It is the most all-encompassing work. It is the most daring book of any scientific treatise ever written.
After the publication of the Principia, Newton is the man. I mean, you know, very few people can understand what this thing is about, but a lot of people can see there's something important in here.
What people saw was that Newton was providing a new framework for understanding the universe, building on centuries of work by his predecessors. Galileo had spent years studying motion on Earth and determined that projectiles always follow a curved path called a parabola. But Galileo believed that motion of celestial objects like the moon was very different.
Galileo still believed that there were differences between the terrestrial and the celestial. He retained the idea that was ancient, that motion was different up at the moon and above.
Newton disagreed. He thought the same laws must govern motion on Earth and in the heavens. To demonstrate this, he would have to devise a set of laws so powerful they could explain motion everywhere. He began the Principia with a set of ground rules, his famous 3 laws of motion.
1.
An object in motion will remain in motion forever unless acted on by an external force. An object's rate of acceleration is proportional to the force exerted on it. And for every action, there is an equal and opposite reaction. These laws allow scientists to make such accurate predictions about how objects move that they are still used today to send rockets into space and explore other worlds. But explaining the orbits of the planets required another ingredient. This brought Newton back to the work he had begun 20 years earlier on gravity. To show how gravity works on Earth and in the skies, Newton designed a thought experiment. He imagined firing a cannon from the top of an extremely tall mountain. From his first law of motion, he knew the cannonball would travel in a straight line at a constant speed forever. But gravity pulls the ball downward. If its speed is low, the cannonball hits the Earth near the mountain. The higher the speed, the farther away the ball lands.
If you throw it faster, it comes farther away. Even faster, farther away. Even faster, it may go 1,000 miles. Even farther, it may actually go almost halfway around the Earth, and there hit the Earth.
Newton imagined that if its speed were high enough, the cannonball would travel all the way around the Earth and settle into orbit.
The orbit of the cannonball around the Earth was a balancing act between the cannonball's tendency to fly off in a straight line and its being yanked back towards the center of the Earth continuously by the force of gravity. So in Newton's picture of the world, there were 2 things. The natural tendency of an object to travel in a straight line, which was true on Earth or in space or anywhere, and there was the attraction of gravity, which was true on the surface of the Earth, and it was true up in space.
Newton's breakthrough was to see that the moon's orbit around the Earth and a cannonball's motion on Earth were governed by the same law of gravity.
That is a beautiful way of persuading you, me, and probably his colleagues that cannonballs falling to the Earth and the moon falling to the Earth is one and the same law of physics, gravity. The moment that he realized that, almost everything else follows from that.
Newton reasoned that if gravity governed motion on the Earth and the moon, why not on Jupiter and its moons, which he had seen with his reflecting telescope? Why not the entire solar system? In a bold leap, Newton proclaimed that this invisible force operates everywhere in the universe.
It's an incredible leap. It's beyond anything anybody had imagined at the time.
Newton called it the universal law of gravitation, and he wrote it in one simple mathematical equation.
It's so important because it really tells us how nature operates in a fundamentally new way. Newton is saying the same thing that is going on in the heavens is going on Earth, and vice versa. It gives us a guidebook to answering the age-old question of what causes the rise and fall of the tides. It gives us answers to the orbits of the planets and their positions. It's a tremendous act of intellectual triumph, one of the great cornerstone pieces of our intellectual heritage.
Another example of circular motion, similar to the planet one, is loop-de-loops. You know, on a roller coaster or whatnot, where you have a cart that is just traveling around, comes into the loop, goes around in a loop, and comes down like that. We can look at this in terms of an object moving in a circle with a bunch of forces acting on it, and because it's moving in a circle, it's going to have some net force component towards the center of the circle that's describing that turn. Now, on the sides here, when it's coming down or going up, its speed's going to be changing. It'll slow down or speed up as it goes around. But at the top and the bottom, at those two instances, it's essentially just turning. It's not speeding up or slowing down. And we can look at those. We'll get to in the next video, we'll start to discuss what happens when it's speeding up or slowing down. But we can look at the top and the bottom speeds and start to ask things about the forces that are acting on them. So if we look at this situation, we can consider, all right, let's look at the cart at the bottom, the roller coaster at the bottom of this loop, right? And we can analyze this using everything we've learned. So at the bottom of the track, we have our object, and what's touching our cart, right? Well, the surface of the track, so there might be some friction we might have to consider. There's a normal force, and that's the only thing touching the cart, and then the long-range force of gravity, right? So we're going to assume, you know, it's not speeding up or slowing down. The wheels are have good bearings in that. So we're going to ignore friction. Just look at the other one. So we have a normal force perpendicular to the surface of the track, and then we have the force of gravity with magnitude mg pointing straight down. Now, we also know that it's turning, so it has some acceleration equal to v squared, v at the bottom, over r, right? So now we can take this and apply Newton's second law. If we look at that, Newton's second law is F net in the r direction is equal to mass times acceleration in the r direction. And we just looked at this. We have normal in the positive direction, mg, gravity, in the negative direction, and our acceleration is the speed at the bottom squared divided by r squared, right? Now, one thing we'll notice here is we don't necessarily know the normal force, but if we know how fast the object's going, we can figure that out from this equation. It ends up being mv squared over r, again, I'll put that b there, plus m times g. So the normal force is equal to G plus V squared over R. And you may all be familiar with this. If you've ever, gone down, if you have skateboarders, you use a half pipe, or if you've ever gone down a hill that's pushed you back up, that normal force, you feel your legs have to push harder on the ground to go up. If you've ever been on a roller coaster or something like that, you feel heavier. You get pushed down into your seat when you're at the bottom, and that's what this is. That normal force isn't just mg times gravity. It's larger depending on how fast you're going. The faster you go, the harder you're sort of pushed down into that surface, right? We can also do the same thing and look at the top of the loop, right? If we analyze the forces there, what are we going to have? Well, we're still going to have the same situation. We have normal, friction, and then the long range force of gravity. We're going to do the same thing where our friction is essentially 0 here. So in that radial direction, our free body diagram looks like this. We have, a normal force perpendicular to that surface. So in this case, pushing downwards. And we have a force due to gravity, mg, pushing downwards. And those are the only forces we're concerned with. Again, we're turning, so we have an acceleration towards the center of the circle with v at the top squared divided by r, that centripetal acceleration pointing downwards. So we can, again, take all of this and look at analyze the forces and apply Newton's second law. So in this case, same thing, F net in the radial direction is equal to mass times acceleration in the radial direction. Sorry, that's an M. If I plug in what I know, well, I have the radial direction is downwards now. Again, radial direction is always pointing towards the center of the circle if we follow the book's convention. So this means the normal force plus the gravitational force, both pushing down, is equal to mass times the acceleration, the speed at the top squared, divided by r, also all going downwards. All of those positive directions. If I solve for the normal force now, I get mv squared over r minus g, right? So that gives me my normal force at the top. And you'll notice if I am going fast enough, this minus sign, this can actually be a negative number if I were just going to plot in any values. But if we think about a normal force, it's a surface pushing on you. So if the normal force is negative, that's implying that for that situation, that surface would have to pull you towards it. And it can't do that. I mean, roller coasters are designed, with like wheels on both sides of the track. So there's actually more forces than a typical normal force. But if you were to think of just an actual pipe and rolling a ball through it or something like that, you can't pull, the surface of a table can't pull you, sort of thing. So this normal force has to be greater than 0, which means there is some minimum velocity that has to be held here, because if that velocity gets small enough, this becomes negative, and it means that cart is going to fall off that loop, and instead of staying in this circular path, it's just going to fall down and go towards Earth, because so we can solve for that, right? We can solve for the minimum velocity that this cart needs to stay on that loop. And the way we do that is we essentially say that this minimum force comes from when the normal force equals 0. When this is at its absolute slowest it can go, gravity is enough to keep this cart moving in the circular path that it's going in. So we can just plug in n equals 0 into Newton's second law, solve for our speed, and we get this minimum velocity. So what that means is the normal force is 0. So we have mg is equal to mv squared, the minimum, squared over r, right? The m's cancel, and what this gives us is the minimum speed that cart can have at the top of the loop is going to be equal to square root g times the radius of that loop. And any faster, and you're fine, but if you slow down at all, that's where you're gonna fall off the track. If you've ever taken, this is kind of a neat trick, if you fill a cup with water, so we fill a cup with some water here, if you take that and hold it and you spin it in a circle that goes upside down, you have to spin it at a certain speed. Otherwise, this water will fall out of the cup if you go too slow. This is exactly what describes that, right? If you go too slow, the force of gravity that is strong enough on its own to keep you in that circle. And if you go even slower, that gravity is actually going to make it turn faster than the circle you're spinning it at, and that water will fall out. Yeah, so again, this is a specific example. It's a canonical one that's often asked in homeworks and various things in this class. But the gist is everything we've done today up to date in dynamics, where we start by identifying forces, to drawing free body diagrams, choosing a coordinate system, and then applying Newton's second law in that coordinate system. We do the exact same thing. All of those skills we learn are still the way we want to think about this. We haven't invented new forces. We haven't done anything like that. The only difference is we are going to use sort of this RTZ coordinate system because it makes our lives easier when we're describing things moving in circles. And the fact that it's moving in a circle gives us a lot of information about that acceleration. Everything else we've learned about forces and that to date is identical. So all of those skills are still really useful. Don't let the fact that we're moving in a circle sort of confuse you.